Hey everyone, today we'll do some previous year GATE questions of solid state chemistry. I collect some questions from previous year questions and we'll learn the concept behind these questions as well. Okay, we'll start with this question. So, this question is the incorrect statement about the solid state structure of CaCl and CaF2, that is calcium fluoride. Okay, so for doing this question we have to know the radius ratio rule, because there some option is that radius ratio of CaCl and CaF2, this one, and is also asks the structure of of CaCl and CaF2 and the coordination number as well. Okay, so what is radius ratio rule? Radius ratio rule. Okay, ratio rule. Okay, radius ratio rule is a ratio of r plus by r minus, is a ratio of the ionic radii of cation and anion. Okay, it's radius of these two radius ratio. Okay, so first one is CaCl, or first we'll learn what is this. Okay, so for this the ratio is comes 1.55 less than 1.55, then the coordination number will be this coordination number table and the structure. Okay, this is structure. So if the ratio is the coordination number will be 2 and the structure will be linear. Okay, if first one is second one is 0.155 to 0.225, that is 3, coordination number will be 3, and structure will be triangular plane. Planners. Okay, 3 will be 0.225 to 0.414, the ratio, then the coordination number will be 4. Okay, and the structure will be tetrahedral. 4 will be 0.414 to 0.732, and then the coordination number will be, the CN is coordination number, that is 6, and the structure will be octahedral. Okay, 5 0.732 to 1, that is coordination number will be 8, and the structure will be cubic, especially the body center cubic lattice, cubic unit cell. 6 will be 1, that is coordination number will be 12, and it will be CCP, means cubic close packing or hexagonal close packing. Okay, this one. So in this portion, this TD or tetrahedral coordination number, the structure example is ZNS or diamond like structure. We read about diamond like structure in my previous video, diamond like structure. Okay, and the octahedral, there is a rock salt, this example like NaCl. Okay, this one have a different, that is some AX, means A is cation and X is anion. Example is CaCl, and AX2. Okay, AX2 and A2X. AX2 is a fluoride structure. That example is CaF2, fluoride structure. Okay, and A2X is antifluoride structure. We'll read what is fluoride and what is antifluoride structure. Okay, example is Li2O, Na2O, etc. Okay, these all comes into this category. Okay, this category cubic, and this one is CCP and SCP extra. Okay, so the radius ratio of this one, so CS Cl radius ratio R plus by R minus, this means CS plus by Cl minus, that is approximately 0.170 angstrom by 0.181 angstrom, that is approximately 0.93. okay, and CaF2 is Ca2 plus by F minus, cation by anion, that is 0.1 by 0.133 angstrom. Okay, that is approximately 0.732 something. Okay, that is okay. So this comes into category, this one, and this also comes this category. So our first option is correct. The coordination number is 8, so this one is correct. Okay, now the structure, CSCl is BCC type structure and CF2 close packing structure. Okay, so CSCl, actually we all know as a basic way that this is, we call this a BCC type structure. BCC means body center cubic lattice. Okay, but actually this is a primitive cubic lattice, because CSCl, how did produce a, okay, this is a primitive lattice or primitive cubic lattice of CS. Okay, and this is CS. Okay, and this is Cl. Okay, this is two are primitive actually cubic lattice. Okay, and these two lattice will come closer and creates that CSCl, and we mistake this as a BCC. But in option, if it is if it is written as a BCC, then we'll and there is no option of primitive cell or primitive cubic lattice, then we'll tick that BCC one. But if the more correct one is the if it is that primitive cubic lattice. Okay, how it is, because if when this these two come closer and these two primitive cell togetherly produce this one is Cl minus and this one is CS. we can tell is as a BCC, but individually this one is a primitive cubic lattice, okay, not BCC, okay. So, and CAF2 coordination number of Ca is 8 and coordination number of F is 4, means 8:4, okay. This is a fluoride structure. This is an fluoride structure. So how it produces fluoride structure means F or this Ca2 plus produces that FCC lattice and F minus occupies the tetrahedral holes or tetrahedral voids. As a result, Ca have 8 coordination number, or and the in surroundings of Ca there is 8 fluorine atom, and of the surrounding of fluorine atom there is only 4 calcium atoms or Ca2 plus atoms. This is an fluoride structure. What is then anti-fluoride structure? Anti-fluoride is exactly opposite of this one. Anti-fluoride means Na2O, anti-fluoride, okay. Anti-fluoride coordination number is 4:8, means cation has coordination number of 4 and anion has coordination number of 8. Here cation have coordination number of 8 and anion is a coordination number of 4, but here it is exactly opposite, so it is anti-fluoride structure and this is fluoride structure, okay. So this is an FCC lattice, creates an FCC lattice, so this option is also correct, okay. This option is also correct one, okay. And this option also correct because CSCl and CF2 the radius ratio we calculated, and this also correct. So this option is not correct because both are not close pack structure. One is BCC and another is FCC, because one is close pack structure, that is the CF2, and this CSCl shows the BCC type structure. So our answer is this one, okay. This is the incorrect one. So we'll go next question. So next question is for an inverse that comes in GATE 2018, okay. For an inverse panel AB204 AB respectively, which one is creates the inverse panel, okay. This is the question hour. So we can see the first option is Ni2 plus, okay, that is D8 system, okay. D8 system means 5 6 7 8, okay. CFAC will be 0.4 into minus 0.4 into 6 plus 0.6 into 2, that is minus 2.4 plus 1.2 minus 1.2 delta 0, okay. This is a negative value. And gallium 3 plus is a non-transition element, so CFAC is 0. So we read that in our previous video that if a non-transition element with a 0 CFAC energy and there is a bivalent or Ni2 plus with means negative, this is more stabilized than this gallium 3 plus. So this will Ni2 plus will occupy the octahedral void, and Ga3 plus or gallium will occupy, means half of the gallium will occupy tetrahedral void and half of the gallium will occupy the octahedral void. So this is our inverse spinel. This is also spinel. We will check the other options also too. This option is Fe2 plus. Fe2 plus means D6 system. Yes, D6 system. And chromium 3 plus. Chromium 3 plus means D3 system. Okay, this one have a CFSE. Have a CFSE. CFSE will be minus 0.4 into 4 plus 2 into 0.6, that is minus 0.4. And this one have CFSE will be this one. CFSE will be minus 0.4 into 3, this is minus 1.2 delta 0. So this is more negative. Chromium 3 plus is more negative, so it will occupy the octahedral void, and this will occupy the tetrahedral void. So this one is a normal spinel. Normal spinel. Okay, this is normal spinel. Zn2 plus Fe3 plus. Okay, Zn2 plus and Fe3 plus. Zn, option number 3, Zn2 plus, D10 system. CFSE is 0. Fe3 plus is D5 system. CFSE also 0. But in this case Zn2 plus is much smaller in size than Fe3 plus. So Fe3 plus will occupy octahedral void and Zn2 plus will occupy the tetrahedral void. This is not a mixed spinel, but in mixed spinel we can see that if the this A and B, if the size is comparable and the CFSE also equal, then we can see the mixed spinel. But in this case the size of Zn2 plus is much smaller than Fe3 plus, so this is not a mixed spinel, this is only a normal spinel. Okay, we read this one in my previous video. And the next one is Mn2 plus and Mn3 plus. Mn2 plus is, Mn3 plus is CFSE 0. Mn2 plus is, sorry, this one not, this is D5 system and CFSE 0. Right, this one D4 system. D4 means CFSE will be minus 0.4 into 3 plus 0.6 into 1, that is minus 0.6. So this one is more negative. Mn3 plus trivalent is more negative, so it will occupy the octahedral void, and this will occupy, all the Mn2 plus will occupy the tetrahedral void. So this is also a normal one. So our correct option is A, Ni2 plus and gallium 3 plus will produce a inverse spinel. Okay, our next question is P, F and I that came in to GATE 2017. PFI represent primitive, face centered and body centered respectively. The lattice type of NaCl and CSCl. CSCl is primitive. We read about that. If there is a primitive in option, then we will take the primitive, not the BCC. Okay, so CSCl is primitive, that is P. And initial structure is face centered, that is F. Correct option is F and P. Initial structure, if we know how the initial is produced, so there is a phase FCC of structure of FCC of Na atom, sodium atom creates an FCC lattice, and also Cl also produce a FCC lattice. Okay, these two, this is of Na and this is Cl minus. Okay, these two FCC lattice come closer and just come just midway. Like if I do it, if this is, I am drawing this Na, this lattice like this one, Na and Cl, if they come this one is here, okay, this one for Na and this one for Cl. Okay, okay, so now what I am doing, okay, now I am creating a new lattice, new face centered lattice. Two face centered lattice come closer and just like this, and we take half of Na lattice and half of Cl lattice and create this NaCl. So two face centered lattice come closer and we just they come and we take on like half of the Na and half of the Cl and create this NaCl. Okay, lattice. So our option is B. Next one, and this came in GATE 2017. The spinel structure of MgAl2O4 has cubic close packing system. Okay, means it is a spinel. The fraction of octahedral and tetrahedral sites occupied by cations means Mg2 plus and Al2. Okay, this is actually a normal spinel. We learned in my previous video that if both A, this is A and this one is B, if A and B both are non-transition element or non-transition metal, sorry, so then the spinel will be obviously a normal spinel. Okay, now Mg2 plus, the question is how much space occupied by these two cations. So this one will occupy the tetrahedral voids and this will all occupy the octahedral voids. So these two actually by this formula we can say that there is 2Al, means our option will be, means in a FCC lattice, okay, in FCC lattice there is 4 octahedral voids and 8 tetrahedral voids. Okay, if I assume that there is only 2 Al atom, means aluminum atom, and there is 1 magnesium atom, so 1/8 means there is only one Mg, so and Mg is occupied by Mg occupies the tetrahedral void, so there is only one, so 1/8 space of tetrahedral void is occupied by Mg. Okay, so tetrahedral size is 1/8, and the octahedral, there is two octahedral, so two octahedral means two octahedral voids, two aluminum occupy the two octahedral voids. So 2 means 1/4, that is 1/2 of the octahedral void will be occupied by this M cation. So our option will be this one, half of octahedral voids and 1/8 of tetrahedral voids. Okay. Our next question that came in GATE 2016. So what is that? When a crystal of sodium chloride are heated in the presence of sodium vapor, they turn yellow. So this is due to the formation of Schottky defects, Frankel defects, F center or H center. Okay. So our sodium crystal is means NaCl crystal is white. Okay, that is white, no color, means white in color. So when you heat in the presence of sodium vapor, means heat in Na vapor, okay, and then it turns to yellow. Why is this one? So the concept is, what is the concept behind this? So if we assume that this is a NaCl lattice, okay, this is NaCl lattice and this is the upper surface of this NaCl lattice, NaCl, okay. So we are heating this NaCl in the presence of sodium vapor. So when we heat this sodium vapor in the presence of sodium vapor, so Na, this, so in the sodium vapor have sodium atoms. These sodium atoms will come this surface to this surface, okay, so NaCl surface, it will accumulated there, and from this lattice Cl minus, okay, sorry, Cl minus from the lattice will come, it will come the upper surface of this, means Cl minus will come Cl minus, okay, this will come to the upper side. The what is happening, that first the Na will come the upper surface of this NaCl, and Cl minus from the lattice will come from the core of the NaCl lattice to the upper that surface. Then Na will leave its electrons and produce the Na plus, and then Na plus and this Cl minus will produce NaCl, okay, this NaCl. And so if the position, and so there is a vacant position of, means so if this Cl minus will go upside, so this position will be vacant, then so this position will be occupied, then this electron that is emitted by this sodium, okay. So what is happening, actually the sodium comes in the upper surface from the lattice, then Cl minus will come closer this Na, and the NaCl produce, and Na will emit one electron from his valence cell, and this electron will occupy that vacant space of Cl minus, okay. So now there is a metal excess defect, means in the lattice the density of Cl minus will decrease, density of Cl minus in the lattice will decrease, and but the density of metal is intact because there is no change of density of metal in the lattice. So there is a defect of metal excess in the lattice, and this is called a metal excess defect. Okay, and it will create a non-stoichiometric initial stoichiometric NaCl. Okay, so now what is happening? Now these electrons that occupied the vacant space of Cl minus, it actually absorbs the energy from that heat, from the energy from the heat, and it will go from ground state to excited state. So it will absorb some energy to go from ground state to excited state. Then again, from when it will come again from excited state to ground state, it will emit some energy that creates the comes as a yellow light. So what is happening? This from the energy of heat energy, this electron absorbs some energy from that, it goes from ground state to excited state, and then it emits the energy and comes from excited state to ground state. That emitted energy will come from the lattice as a yellow light. So this center is called epicenter. So the formation of this is due to the formation of epicenter. The center is called epicenter, means the center. Which center is called epicenter? That is the center that occupied by the electron, the vacant space of Cl minus, that is occupied by electron, that is called epicenter or Kähler center. Because for this center we are getting this yellow color, that's why it is called Kähler center also. So our answer is option C. Our next question is that came in GATE 2020, very recent question and very basic question also. So what is that? Consider that AgX crystallize in rock salt structure and the density is 6477 kg meter cube per meter cube, and the unit cell length, that is A, is 577.5 picometer, and the atomic weight of Ag is 107.87 gram per mole, 107.87 gram per mole. So atomic weight of X in gram per mole, and the rounded of 2 decimals place. So we have the density and the unit cell length and atomic weight of Ag. We have to calculate the atomic weight of X. Okay, so what is the formula? Density rho is equal to Z dem by Na cube. Okay, what is Z? That is number of atom, or here number of molecule. Why I am saying molecule? Because AgX is a molecule present in a unit cell, that is, it creates a rock salt type structure, and we read that our rock salt type structure coordination number is 6, that is NaCl, and NaCl creates the FCC, and in FCC we know that there is a number of atom is 4, so here Z will be 4. N is Avogadro number, A is the unit length, and M is the atomic weight of the AgX. We have atomic weight of Ag and we have to calculate the X. So here we calculate the M. Okay, now then M will be density into M into A cube by Z, that is 6 4 7 7 into 10 to the power 3, that is kg per meter cube. I am saying that is gram per meter cube. Okay, N 6.023 into 10 to the power 23. There is no unit of that, or we can say that is as a mole. Oh, A is means we can, the unit can be written as a per mole, and A has 577.5 into 10 to the power minus 12 meter cube, so it is meter cube, and by Z is 4, so meter cube cancel out, we have gram per mole. Okay, if we calculate this one, so we'll get 187.83 gram per mole. Okay, that is M, means that equal to atomic weight of Ag plus atomic weight of Ag plus atomic weight of X. Okay, so we have a, so atomic weight of X will be 187.80 minus 107.87 gram per mole, that is 79.96 gram per mole. That is our answer. Okay, so these have answer. This one very easy, but the calculation is that much lengthy calculation, but this very much easy question. So you solve these questions. There are many questions, and we also in future we will collect also this type of question, and we will revise our concept again. So by this I am ending this session. Thank you.